Hey, testing, testing. All right, we're going to get started here. Welcome to this ISTEC Distinguished Lecture. Before we get going with the lecture, let me say a few words about ISTEC. ISTEC is CSU's Information Science and Technology Center. We deal with all things related to information technologies, ranging from education, research, and outreach. One of the activities that we hold on a regular basis is the ISTEC Distinguished Lecture Series, of which this is one of the lectures. But without further ado, I'd like to introduce to you Indrakshi Ray from the Department of Computer Science, who will introduce to you our distinguished lecture for today.
So, first of all, I'd like to thank ISTEC for, bringing in Dr. Fred Schneider, who's one of the greatest computer science of our times, I'll just, to keep it short, Professor Schneider is the Samuel B. Eckert Professor of Computer Science at Cornell. He joined Cornell in 1978. He did his PhD from Stony Brook and his bachelor's from Cornell. He has, his research spans a number of different areas. Programming languages, fault tolerance, security, distributed systems, logic, quite a wide spectrum. And he has he's a AAAS fellow, IEEE fellow, and he also is a member of the National Academy of Engineering. He has won many awards for his work in distributed and trustworthy computing. One of his papers was the SP Hall of Fame Award for seminal research. And the most notable is the IEEE Emmanuel R. Peer Award. And another person who basically comes to mind who has won this award is Shafi Goldwasser. So, you might very well be seeing the next, Turing Award winner. And he's also very active with the, he's testified in the US House of Rep in the Armed Services Committee. He's chaired the National Academy's Computer Science and Telecom boards, and he's a founding chair on cyber resilience. And he is a great, he's a great advocate of computer science in the government, and is very interested in getting, smart minds into policies and governance, and he is a great mentor. I first met Fred in 2004, and for a AFOSR PI meeting, and there were a lot of researchers from Cornell, and I was trying to, in my mind, think that all the presentations were very harmonious, and it appeared to me that Fred's hand was behind it, like. It was like so well, choreographed, I would say. And so he's been the chair of Cornell from 2014 to 2018 in the computer science department. And he's really one of the greatest computer scientists of all times.
Thank you. I won't live up to that, but I will try. It's an honor to be here and have a full house to talk to you about laws. Depending on what community you come from, law means something different to you. If you're a scientist, then laws tend to be primarily inductive in nature. That is, based on experiments, you come up with some conjecture about how reality works, and the only thing you get to do is try to falsify your law. You can never prove that the law is correct. All you can do is falsify it. E equals mc squared is an example of such a law. Mathematicians come up with laws, and this is a deductive as opposed to inductive proposition. One starts with a set of axioms and some inference rules, and you apply the inference rules to the axioms and see what you can conclude. So you can prove things. It's possible often to disprove things, and it's easy to come up with laws that are simply irrelevant because the axioms may not describe anything having anything to do with reality. And then there are civil laws, so lawyers and policymakers worry about that. And the good thing about civil laws is they're subject to interpretation. That's what, among other things, the Supreme Court does. The law says one thing, and somebody has to say whether it applies to a given situation. And the reason we pass civil laws is because it's a way to change the way rational actors will behave. And when other means are not available to change behavior, perhaps for societal good, then passing civil laws is a way to proceed. What I want to do today is have a look at how these kinds of laws might work for cybersecurity. I'm going to say very little about scientific laws and mostly focus on mathematical and civil laws for reasons that will become clear. But I want you to come away with a sense that laws are a good, nice end product for research or thinking. So as computer scientists, you may think in terms of theorems and artifacts as an end goal, but you might also think in terms of laws. So there's one very easy scientific law for cybersecurity, and that is the law that every system can be compromised. I don't know of anyone who can give me a system that doesn't satisfy that law. And it's not a very interesting law. I'm sure none of you are surprised. And laws that are unsurprising are not useful. Right? Information content has to do with surprise. Where we would benefit from laws in cybersecurity would be laws about people or laws about things. Laws about people, that would give us some insight into why people tend to click on those links in these odd emails we get that are essentially phishing attacks, right? We haven't been able to figure out a way to convince people not to do that. And I don't think it's people's fault. I think it's our fault. But some laws about that, or laws about picking good passwords and so on. So we do need that stuff. I'm going to say very little about it because I don't know much about it. There is an important role for it. Let's talk now about mathematical laws for cybersecurity. And the structure of how this would work is laws are usually relative to some abstraction of reality, a model. And the model is a precise description of something. If it's a precise description of reality, it's only because somebody has some scientific laws that is inductive that argue that this model is an accurate description of reality. So there's no way to prove that your model is accurate. I just hope you would look at the model and be convinced it's representative. And then from that model, there are various techniques. You can use logic or mathematics or game theory from which you can extract interesting truths from the model, and you would like those interesting truths to provide something valuable. In our case, something valuable is a way to help in the design and construction of secure systems. So let's talk a bit about what is the specification for a mathematical law to satisfy for it to be useful. Recall, I said that there is a risk that a mathematical law will be irrelevant. And so we'd like it to predict something of interesting. Laws are valuable because they give us a way to predict things that we wouldn't have known about otherwise. But most people with laptops have a way to predict things. With a laptop, I could predict how the computer will respond to just about any input. And so, if you will, a laptop embodies a bunch of laws about, depending on whose you bought, a bunch of laws about Apple hardware and the Apple operating system, or Intel hardware and the Windows operating system. So laws about that laptop, which embodies many, many truths, many that you'll never know, aren't very interesting because they're only about a specific system. So to become useful, we'd like a law to be something that transcends a specific system. So not only about Windows 10 on a particular Intel processor, but about any operating system on any processor, or any piece of software on any computer. And we'd like the laws that are about attacks to be about big collections of attacks rather than the specific Spectra or meltdown attack or some specific buffer overflow attack. We've, of course, like our laws to be applicable in real settings. It's easy to prove theorems about Turing machines. Computers are Turing machines, so you might think we would have a law about security of computers, but it's not clear that laws about the security of Turing machines will be applicable in real settings because things get more complicated. The physicists have shown this with quantum theory. They can tell you interesting things about very small atoms, but they can't compute interesting things about complicated things like tables because the real system is so much bigger and the mathematics involved gets out of hand. And if we're good about the laws we design, they not only will predict something, but they'll provide explanatory value. This is a university. It's the business of universities to teach people how to think. And one way to think is to learn abstractions that you can use to talk about stuff so that you can ignore irrelevant detail and you can understand significant interactions. And so the extent to which these laws give us abstractions or talk about connections and relationships, then it elevates the level at which we think, and that's generally good. So if we wanted mathematical laws about cybersecurity, what would these laws be about? So I submit that they would be about three kinds of things: attacks, defenses, and policies. And specifically, they would be about relating classes of attacks, defenses, and policies. So you might have a law that says this class of defense is sufficient for defending against this kind of attack for these policies, right? And that would tell you what the defense was good for and what it wasn't good for. Or we might have a law that says if you combine this kind of defense and that kind of defense, the result is better than either one. People talk about defense in depth as a way of enhancing the security of a system. Or we might have a lock on the front door and a lock on the safe. And is that better than having just a lock on the front door or a lock on the safe? Well, you have a sense that it is. How about the case where I have two passwords to get in? Is that better than one password? Or what if I encrypt it twice? Is that better than encrypting it once? Well, the chances are, for some encryption algorithms, the standard AES algorithm, encrypting it twice is not better than encrypting it once. So you want to know when you can combine defenses and do better. So that's the kind of laws that I would aspire for us to have in laws for cybersecurity. So let me spend a little time talking about classes of policies, attacks, and defenses. And my purpose is not to tell you what are good classes. Rather, my purpose is to show you that it's a research problem to figure out interesting classes. And so the premise of cybersecurity, that is what you learn in a cybersecurity class, is not good enough to embark on this enterprise of building laws. So a policy is generally seen as a description of what a system should do and what it shouldn't do, right? It should allow me access to the data. It shouldn't allow my adversary access to the data. And if you look at a modern security text, the set of policies is usually described in terms of this so-called CIA denotation: confidentiality, integrity, and availability. And actually, this dates back to the 70s to, believe it or not, a NASA report about what they were interested in. So confidentiality is about who is allowed to learn some piece of information. Integrity is about who's allowed to change it. And availability is an assertion that the information should be available. Despite the fact that this is the basis for modern security, it's not really a good basis for the kind of laws I think we should be building. And let me explain why. First, it's not rigorously defined. If you try to formalize confidentiality, it turns out to be really tricky, and it's easy to figure out counterexamples for your definition. Many people have tried. For example, if I don't let you access to the information, am I keeping it confidential? Well, maybe not if you can deduce the fact by looking at something else. Right? So the fact that we could detect that the US was going to launch an attack on a foreign country the next morning by noticing the number of pizza truck deliveries to the Pentagon that night, were we keeping the attack secret? Well, maybe, but maybe not. The reporters figured it out. And second, CIA are not orthogonal constructs, and this is what's the most troubling part about them to me. You would like them to be independent. You would like achieving confidentiality to have nothing to do with integrity and so on. Let me argue that they're really quite closely related. Suppose I want to keep a piece of data confidential. One way I might do that is prevent you from accessing it. Another way I might do it is by changing the data and letting you access it. Now when you get the data, it's nonsense, and so you didn't learn the real value. So that's an example where I can use integrity attacks as a basis to achieve confidentiality. Or I could prevent you from accessing the data because there's just no way for you to get to the database, make it unavailable. So I can achieve confidentiality either with integrity or availability. That's not good. Think about how the color spectrum works, right? Red, orange, yellow, green, and so on. Those are independent colors, right? There's no way to get one of them with the others in a simple scheme. Or think about multiplication and addition. So we have this nice partitioning of ideas, and that partitioning is not possible with CIA, and that's why I think they're going to be of limited use. Attacks. In order to define attack, I need to say what a system is. For us, a system comes with a set of interfaces, and the interfaces are the sole way by which you can change the state of the system or learn anything about its state. Most people will think of the interfaces to their laptop as the keyboard and the mouse. They'll think of interfaces to software as the routine names and parameters you can invoke it with. That's a subset of the interfaces, but among the other interfaces are I might be able to notice how long it takes to do a computation, right? That tells me something about operation. I might be able to listen to the radio frequency emanations of the device and learn something about it. I might be able to monitor the temperature. I might be able to take a picture of your eye and notice a reflection of the screen. So when I say interfaces, I mean all those interfaces. And most cybersecurity experts only pick a subset of the interfaces and worry about it. And then we read about attacks where the attacker used a different interface. And so there's some set of issues there. But if we define a system to be a set of interfaces, we can define an attack to be some input to some interface that causes the spec to be violated. And that's a pretty general definition, and I'm comfortable with that definition of system and attack. I'm not comfortable with the usual definitions of attacks like buffer overflow attacks, right, or side channel attacks, because these are wedded to specific mechanisms. I would like, if we're going to have laws, for us to have laws that transcend that. So examples of interesting classes of attacks, but I think this doesn't span the space by any means. Something like, what are the classes of policies that can be disrupted by submitting requests, so denial of service attacks? Or if you want to look at the class of interfaces, then side channel attacks are about classes of interfaces. Or you might define classes of attacks in terms of how much capability the adversary has. Crypto algorithms are examples, use these PPT adversaries. If you look at the defense literature, they distinguish between attacks that happen because the adversary took some software off the web versus attacks that happen because the adversary could look at the artifact and design an attack versus attacks that happen because the adversary could disrupt the supply chain that produced the artifact that's being attacked. So that has to do with the amount of resources. So those are more interesting classes of attacks than the single attack that one sees typically in security conferences. And finally, defenses. The usual way to think of classes of defenses is a defense is a way to make some policies hold. Let me suggest a different definition, and that is a defense is a way to relocate what has to be trusted. So I add a defense so that I don't have to trust something else, but I end up trusting the defense. So when you put a firewall in a system and it prevents certain packets from reaching the system, you don't have to trust the system to do well for those packets because they're not going to get there, but you do have to trust the firewall. So I've relocated what's trusted. And if you do that, you can take the view that security engineering is really an issue of moving the dirt around under the rug. It moves what has to be trusted to something you feel is you're more comfortable trusting. That could be the basis of an engineering discipline, whereas the other definition of defenses, which is it makes policies hold, doesn't help me understand about engineering trade-offs. And if you look at the literature, you'll find there are really only four basic strategies for defenses. I'd love to be able to prove a law that says all defenses are instances or combinations of these strategies. I don't know how to do that proof, but I nevertheless can suggest what the categories are. Some defenses work by monitoring, see what gets submitted. If it's okay, let it proceed. If it's going to violate the policy, block it. Some defenses work by creating isolation. If two things are isolated, then no matter what the adversary does to one thing, it can't affect the first. The recent Spectre and Meltdown attacks are about violating isolation. Some attacks work by making assumptions of independence. One thing affecting it doesn't give you any insight into how to affect something else. So when we run replicated copies of the system, but the different replicas are running different systems, then it's harder for an attacker to succeed because the attacker has to do twice as much work. That's expecting independence. This two-factor authentication that is becoming standard, that's about independence. Finding out your password is not the same thing as finding your phone, and so the attacker has to do twice as much work. And some strategies work by asymmetry. It's hard to do something unless you know some secret. And if you know the secret, it's easy. That's how much of cryptography works. So those are the classes of defenses. So armed with this desiderata about attacks, policies, and defenses, the way I'm going to try to convince you that there could be laws for cybersecurity is to look into history and show you some examples of things that I think qualify as laws. And I hope this will inspire you to think about your work in terms of laws, but also to devise new laws. So I want to look at three examples. They're examples that are one way or another close to my heart. They're not the only examples from history, but I have only a short time to deliver this lecture, and therefore I can't go through everything. So think of this as a random subset. The first law I want to talk about has to do with access control. In the 60s, people started to build time-sharing systems. In fact, it wasn't until we decided to share computers that we started to need security. When computers were shared, then there was this possibility that one computation would interfere with another. And time sharing was a great way to share computers. And there were two time sharing systems built about the same time at MIT. And one introduced the idea of access control lists, and the other introduced the idea of capability lists. An access control list associates with a resource like a file a list of the users that are allowed to access that file and the access modes each user is allowed. Those of you who have familiarity with Unix or Windows know what an access control list is, because that's how file security is done. The other way to do this would be to associate with each user of what was called a capability list. And the capability list was a list of the resources and accesses that that user could have. So a capability was an unforgeable ticket. When you go to the movies and they give you a ticket to get in, that's a capability. Okay? And if you wanted to pass an access, you would pass the capabilities. So both of these systems were developed, and in those days, so this is the dark days of the 60s, there was this debate about which one was better. Right? There are two separate mechanisms for doing access control. Butler Lamson, who was in the middle of helping to design the standard curriculum for an operating systems course, sat down and said, you know, we could describe access control by writing a kind of table, which he called a matrix. And the rows would correspond to the users, the column would correspond to the resources. And notice that a row is a capability list, and a column is an access control list. That's the proof that capabilities and access control lists are equally expressive. So this is proof by notation, or this is proof by designing an interesting abstraction. And if you will, that's the kind of thing we'd like to do, figure out the right abstractions that make things apparent. Now, there are some important practical engineering issues that distinguish between access control lists and capabilities. So you can still have that debate. But in terms of who gets what access, it's now clear, proof by picture, that they're equivalent. And the next big step, I would say, in access control laws was in 1975. So this is some years later. And the question was, in this matrix, is it possible for Bob to do something to get some additional accesses based on invoking an operating system operation? Harrison, Ruzzo, and Ullman proved a theorem that you can't build a program which will analyze the rules for changing the matrix and predict whether a given user can get a given access. So that says if you run a system with its initialized state, and you want to know if eventually some principal will get a given access, that's not something for which you can build a general testing system. And this is just as disheartening as the fact that you can't build a program that will detect whether some other program has a bug in it. It's the halting problem, and this proof is the same thing. So this isn't an important practical result. I mean, it does mean if you're working in a company and your boss comes and asks you to build the system that's going to validate all of their security access control systems, you can say, no, I shouldn't bother. It's an undecidable problem. But what's interesting about it is it's the first time we see security being proved by reduction to a halting problem. This is vintage theoretical approach, reduction, and security is now as legitimate as other pieces of theory. And there's a special case for simple enough operating systems, you can decide it. Okay. So remember, I started with this picture that the landscape of laws is in terms of attacks, defenses, and policies. And what I've done is I've shown you these 2 points in that space. There are lots of points in the space, but those are 2 examples. Let's look at another set of examples. Looking at the history of physics, you see that fidelity of the model to reality ends up driving lots of developments. And the example I want you to think about is the laws of motion, according to Newton, were pretty simple. And it's what we teach most people in high school physics. But they're wrong if you happen to be traveling close to the speed of light. And that gets you to special relativity and so on. So what happens is we added a model that had more fidelity to reality. In fact, it's only recently that we established that these laws are good models of reality with some experiments. So the more refined, careful look at modeling reality causes us to change the laws. And the laws of motion still work pretty well for the speeds that you and I go, but if you're going to do anything fast, you probably wouldn't want to use those. So I want to talk about laws of information flow. And in the 60s and 70s, there was this concern about information that was tagged with labels, and based on the label, the information was accessible or not. So you had to have a secret clearance to read information that was classified as secret or public. You had to have a top secret clearance, then you could read top secret, secret, and public. And there was a set of laws about that simply said you're not allowed to read up and you're not allowed to write down. You can't read something higher than your classification. You can't write a value to something that's tagged lower. And this information flow theory was wonderful, but it said nothing about integrity. And in connection, actually, with figuring out how to put the launch codes in the missiles that we had in silos, we didn't want some spy to come in and change them. Military security folks became concerned about integrity. How do we make sure that somebody doesn't change the launch codes so the missile is going to end up in New York instead of in Moscow? And Ken Biba came up with a result that said the same rules that work for confidentiality, right? No read up, no write down, are the dual of the rules you want for integrity, which is, so you order integrity, and there's highly trusted data and untrusted data, and you shouldn't write from untrusted data into trusted data. And that's a duality. And so this was wonderful. It's a nice law. It says integrity and confidentiality are duals. And more recently, people have looked at quantifying things. So for confidentiality, we could quantify how much information leaks, as opposed to saying you're not allowed to leak information. And so you would write down confidentiality in terms of entropy. And Mike Clarkson and I came up with one scheme. There have been many schemes. And it occurred to me, ever interested in changing the world, that if I had a set of laws for measuring confidentiality leakage, then one could use Ken Biba's duality and have a set of laws for understanding corruption, amount of corruption. So it's not just integrity in a qualitative way, but integrity in a quantitative way. So the picture here for confidentiality is a user labeled secret is not allowed to have information flow to an attacker who has labeled unclassified. That's what confidentiality rules out. And if you make it, if you quantify it, then what you want to know is that X, how many bits are flowing. And the integrity case is the attacker's not allowed to submit inputs that affect the user. That would violate integrity. And to quantify it, we would know how many bits of corruption. And so that was the way this result was going to work. And the result now is so the dual of confidentiality leakage is something we might call contamination. And I would think that we are done, but we're not. Because an attacker, by submitting information, untrusted information, can, instead of corrupting what the receiver gets, simply jam the channel and prevent less information from flowing. So there's this other phenomenon that once you start worrying about measurement, you have two quantities. One is the suppression and the other is the contamination. So here's another example where we looked at a higher fidelity model, and it changed the laws. And in particular, the new law is this thing called the LS theorem, which says the amount of leakage plus the amount of suppression is always a constant. Okay? So you can increase the leakage or you can increase the suppression, but you can't increase both. That holds for anything that does declassification. An attacker who is stealing stuff is doing declassification. So this higher fidelity model led to this very simple rule, and actually the LS theorem is stated in a simplistic way. That's not a PowerPoint mathematical formula. That's really what the theorem is. You just have to instantiate the three words there with the information theory function that is the number of bits. And if you have this theorem, then you can go look at the literature on database anonymization. Right? This is all the rage. How do we prevent people from learning things by scanning databases statistically? How can I prevent you from asking the database that describes everybody's information, right? And learn something they shouldn't? Then you either anonymize results by returning slightly inaccurate values, differential privacy, or you anonymize it by preventing certain questions. And you can look back at all of those papers which give bounds, and they all are easily derived if you derive them from the Ellis theorem. So this is a way to unify a whole lot of diverse results, and that's the kind of thing I'm hoping that laws are going to do. So I just talked to you, I just populated more points, and the important thing about what you just saw is that was all about policies. It wasn't about defenses. It tells how policies interact. Let's look at one last example of these cyber laws, and that has to do with defenses, right? So a very important class of defenses dates to 1972. The idea of a reference monitor. A reference monitor sees requests. If the request would violate the policy, then it blocks it. And the mechanism that's seeing requests and blocking them has to be somehow prevented from being subverted. That's an integrity property. And reference monitors are everywhere. The virtual machine mapping hardware, virtual memory mapping hardware in your computer is a reference monitor. A firewall is a reference monitor. The operating system kernel, when it checks your file access requests against the access control list, is a reference monitor. And I can think of very few implementations that don't involve reference monitors. And what's interesting is up until 2000, nobody had asked, not nobody knew, but nobody had even asked, what is the class of security policies you could enforce with a reference monitor? Which seems like a good question to know, because if somebody comes in and asks you to build security, you'd like to know if you could stick a reference monitor someplace and have the job done. So that wasn't a question that had been asked, and I stumbled on it. And if you look at the essential attributes of a reference monitor, that is, it makes its decision based only on what it's seen. That is, it makes the decision based on what it's seen, not what other possible executions could have been. And it has to reject based on that. Then you can prove that the class of defenses that work by looking at the prefix of execution, these prefix close sets, are what reference monitors enforce. That sounds trivial, but it turns out that class is known in the semantics literature as safety properties. And you may know that every property is a conjunction of a safety property and a liveness property. That should tell you there are some things that reference monitors cannot enforce because they're liveness properties. So once we have this theorem that monitoring is the same thing as safety, then I can tell you about policies that cannot be enforced. So things like X is not correlated with Y is not a safety property. You can't tell when you look at a value of X whether it's changing according to Y. You need to look at least two executions to know that whenever you change X, Y changes. Whenever you change Y, X changes. And so a reference monitor that only gets to look at one execution can't do that. That, by the way, correlation is the same thing as information flow. So I just told you you cannot achieve strict confidentiality with reference monitors. You can achieve something more draconian, but not something exactly that. So now we have a basis for ruling out policies that we can't do this way. Moreover, it turns out we could use the literature of safety properties, and safety property literature says every safety property corresponds to an acceptor, which looks like a finite state automaton. This is just the thing that accepts those prefixes that are okay. So this particular automaton is for the policy which says you're not allowed to send a message after you've read a file. Probably that's the policy you'd like your laptop to have if Microsoft sends a program down to check the configuration. If it's read one of your personal files, you'd like it not to send a message back to Redmond because it's leaking some stuff. Given that every safety property corresponds to an automaton, we now have a new way to do enforcement. And that is, take the program, right before every statement, copy in code that implements this automaton, and have the automaton stop the execution if the next statement was going to violate it. So essentially, we can do inlining of reference monitors. And what that does is it relocates trust from the program to the program that inserted the reference monitor. So this was at the time a new class of enforcement things. Inline reference monitoring now was widely used. And it followed directly from constructing this theorem about what's enforceable. So this class of what's enforceable then spans defenses and policies. There are other examples of this, like using address space randomization or this rewriting things in random ways. What class of attacks does that defend against? And we know the answer to that, and you could look at various things. So what I hope I've done is given you some sense about what laws look like. They resemble standard security defense mechanisms and attacks that you might see in a class, yet it presents it in a somewhat different way, and it gives you some insights about reality that you might not have had if you took an entirely mechanistic view. So civil laws are the last thing that we might talk about. And the trouble with civil laws is you can read them and they all seem like they're point solutions to various problems. And there's some risk that combining these point solutions will lead to incentives for the wrong behaviors. And this was a worry for me more a decade ago when there was a Congress that was actually able to pass laws than today. But I still think it's a concern we should have if we're ever going to come up with legislative or regulatory solutions to cyber. And if we don't invest in that, then the incentives that will cause people and companies to build into their systems the right stuff don't exist. So while technology is important, I believe without policy, we're never going to solve this problem. So that led Deirdre Mulligan and me to think about what would be the overarching way to relate laws and convince yourself that you were doing the right thing. And this led to the notion of what we call a cybersecurity doctrine. And it is a set of goals which say what you're trying to get, and a set of means which say what's allowed in getting them. So a doctrine comes with a set of goals and a set of means. And it sounds like a straightforward meta-abstraction, if you will. And the question is, how do you convince somebody that it's a good way to look at the world? And so one way is to use history. And we could go back and look at history and see whether we can explain what was going on in terms of doctrines. And that's nice, but that's revisionist science. And the best case would be if I also could invent something new, because I'm asking you to think in terms of doctrine. So I'm going to do both. Let me look at history. And if you look at history in the 60s, when the Defense Department first became concerned about cybersecurity, they realized that the problem was that big systems had bugs in them. That was the basis for attacks. So if only we could build systems that were perfect, then we wouldn't have to worry about problems. And that led to big investments in program verification. Because if you could prove the system correct, then it wouldn't have those flaws. And the trouble, so the doctrine of prevention was what was driving that. And the doctrine was, let's build, the goal was systems that don't have vulnerabilities. The means were whatever means we could do to build correct systems. And the trouble was, for big systems, it was hard to get the spec. They were big, so it was hard to do formal verification. It's hard to verify a 10,000 line program, much less a 20 million line program. You couldn't test them. If you had performance standards like it worked or it didn't work, that would require some way of measuring security, and we didn't know how to do that. Even if we succeeded, it would ignore the possibility that attackers would do social engineering, phishing attacks, which is the largest form of attack today. And every time you upgraded the system or added a program, you'd have to do verification again. So it really wasn't feasible. So we know it failed because this isn't the way systems are built. And it's clear why it failed, but it's a doctrine and it explains about a decade worth of work. Because it failed, that led to this doctrine of risk management, which said, let's only make investments in the small part of the system that's concerned with attacks. And so people talked about figuring out where to make investments and what not to make. And that required you to know how much how much damage an attack could do. And there was no way to agree on the value of confidentiality or integrity. Most of you all think you're interested in privacy, but most of you also tell the grocery store exactly what you're buying every time you go, and so on. And we also had no way to know what the probability of an attack was, so we couldn't do expectations. If you don't do expectations, you can't minimize anything. So that wasn't workable. It meant you were worried about a smaller part of the system, so it addressed that, but it wasn't workable, and that's what has come to be. And the next doctrine, and this is one that you still hear about, was the doctrine of accountability, which is oversimplifying. Let's put somebody's name on every packet in the internet. And if the packet is evil, we'll go arrest them. And because they know they're going to be arrested and thrown in prison, they won't send evil packets. And there are many problems with this. One is it's hard to know where the packets really came from. The fact that it came from your computer doesn't mean it came from you. Maybe there's a bot running on your computer. You don't understand all the software that you're running. What if the packet came across the border? I can't arrest somebody in certain countries. It really says nothing about privacy. It presumes attacks are crimes. Well, maybe attacks are cyber warfare. And so this doesn't work either, and I'm happy to see that the various proposals for people to do this kind of strong attribution have not led to law. So here, that brought us up to the current date. That's a quick history of law, cyber law, through the lens of doctrines. And then my challenge is there something new that we could propose based on the idea of a doctrine? And there is, if you realize that cybersecurity is what economists call a public good. Right? A public good is something that's not rivalrous and not excludable. The fact that you have cybersecurity doesn't mean I can't have it, right? Having a piece of pizza, if you have it, I can't have it, right? So that's different. But this is something where letting you have it doesn't cost me anything, and I can't prevent you from having it if you have it. And the economists have a whole lot of stuff for things that are called public goods. And the best known public good is public health, right? So public health says we want the doctrine of public health, and we all live this way, and there are many laws that have been passed in support of this. And the goals are prompting the production of health or managing its absence. And there are lots of means that we use. Wash your hands, and when you have a dreaded disease, you report it up to the CDC and so on. So what isn't public health? Keeping our president healthy is not a piece of public health, right? One way to get health would be, let's only make sure the leaders stay healthy. That's not what this doctrine says. It turns out if we maintain health generally, the chances are pretty good that our leaders will be healthy. But that's the difference between specific health and public health. And public health has very interesting trade-offs, right? So the doctrine of public health says everybody ought to be, our doctrine in the US, every kid has to be inoculated against certain diseases before they go to kindergarten. Right? So great violation of privacy, we stick needles in our kids so that we can have herd immunity. That's the kind of trade-offs that we make. So we pay a price in support of this. So if you know about public health, and that was a 30-second introduction, then there's a very slick analogy between public health and cybersecurity. Instead of worrying about people, we're going to worry about the network. A positive state would be the positive state of producing cybersecurity. Instead of managing disease, managing cybersecurity, that means when there's an attack, you figure out a way to take it down. And so the doctrine of public cybersecurity, this new regime that we're proposing, is to prompt the production that you do with regulation. You accept the fact that there's going to be security and you figure out a way to manage it. And you have to agree on a balance between costs, which are going to be individual rights. In the case of public health, it was getting stuck with a needle before you go to school, versus the benefit, which is the public welfare. That's a dialogue that hasn't happened in the last, say, 3 or 4 years, the post-Snowden era. I think there has been a lot of public discussion about what we want from privacy and how it trades with security. People who regret having the government monitoring who we call versus the view that some have, which if we kept track of this, then we'd be able to prevent another 9/11. That's a trade-off that isn't right or wrong. It just requires people to come to some consensus. And the doctrine of public cybersecurity says right out front, you need to have those discussions, and that new laws ought to be justified in terms of this vocabulary. And so that's a meta principle, if you will, for law in cyberspace, much as the earlier stuff were meta principles for technical things. So that concludes my comments. I'll leave you with what I talked about came from a bunch of papers, and the citations are there, and I'm happy to take questions if there are any.
So Fred, one thing I didn't, and maybe I missed it, but it didn't seem to me that your talk touched much on the notion of identities and multiple identities, which I keep finding as a thread in many of the security issues. Is there a similar sense of a law related to identity in this space or not?
I don't have, I can't cite a law, but the use of multiple identities is a double-edged sword. We know that lots of attacks are possible. Fake news is possible now because stuff is coming from multiple identities. On the other hand, one theory of privacy, it's not the one I happen to embrace, but it's a theory, says you, the physical person, actually embody multiple identities. There's Craig, the department chair. There's Craig, the father. Craig, the the sportsman, and for each of those identities is a set of attributes. And when you participate in an activity, you come with that identity. Other people should not learn about other identities of yours. They're independent. And so it seems clear to me that clarity on what a principal, PAL, what the players are, is important, and identity seems to be a good abstraction for that. But I can't say anything beyond that.
Other questions? You have a question? No. Oh, okay. So I have a question for you. Can you go to slide number 9?
Oh my. Actually, I think this works.
So, you have talked about 4 major strategies, basic strategies.
Yes.
Where does deception fit in this group?
Deception is asymmetry. So
Okay.
deception is because you don't know something, it would be expensive for you to figure out the reality,
I see.
you get misled. Right? So deception is no different than not knowing a false key. Right.
Any more questions?
All right, before we end, we have a token of our appreciation for our distinguished lecture today. Let me read from the plaque here presented to Fred B. Schneider in appreciation for your Information Science and Technology Center ISTEC Distinguished Lecture, Colorado State University, October 22nd, 2018.
Thank you.